Now we will see the designing of M-derived low-pass filter and how we are going to overcome the disadvantages of constant K filters using M-derived filters. Because to avoid those disadvantages only these M-derived filters are introduced. And what is the main disadvantage there? We are unable to get the sharp attenuation, sharp change in the attenuation or rapid change in the attenuation. So let us see how we are going to overcome using this M-derived low-pass filter. So if you see, we can even take T section or pi section, anything can be chosen. So it is showing the M-derived low-pass T and pi filter, and at a particular frequency the shunt arm of the T section or our series arm of the pi section will be in resonance, and it is going to give the short circuit to the input in case of T section and open circuit for the pi section, causing infinite attenuation. So this is the important logic or statement behind the designing of M-derived low-pass filter, because when there are two different impedances and if we have inductance as well as capacitance presence in that, so there we are going to get series resonance since they are connected in series. Okay, that means here we will be getting the series resonance at some particular frequency which is called as resonant frequency. Also, if we consider pi section with the combination of these parallel impedances, we will be getting parallel resonance. So what happens during the series resonance? We all know this becomes short circuit, and in case of parallel resonance the entire combination becomes open circuit. Okay, so that causes infinite attenuation. So if you see the attenuation formula for symmetrical T section or symmetrical pi section, there is some formula, right, in terms of Z1 Z2. So if you substitute this short circuit in that formula, you will be getting infinite attenuation. And here also if you substitute this infinite in place of this particular arm resistance or impedance, again you will be getting infinite attenuation. That's why this sentence is given, which is very important. So this is the logic behind the designing of M-derived filters. So you better understand it, read it. Fine, right. So suppose if Z1 is chosen as j omega L through an inductor element and Z2 is chosen through a capacitor element, then Z1 Z2 can be written like this. Then at resonant frequency what happens? The reactance of inductance will be equal to the reactance of capacitance. When you perform that action, you will be getting resonant frequency. So here omega naught will be equal to 2 by square root of LC into 1 minus omega square. So what's happening at resonant frequency? At resonant frequency attenuation is becoming infinite. So the same thing is written here. So here F infinite indicates the frequency at which the attenuation is infinite, which is nothing but resonant frequency. That's why they are made equal to each other. Fine. So this is the expression. When you substitute 2 pi f naught, that 2 pi will be coming down. So you will be getting this simplified expression. So now we also have for low pass filter, the cutoff frequency is 1 by pi root LC. Fine. And now we got f infinite, which is equal to 1 by pi root LC into 1 minus m square. So when you relate these two, you will be getting this expression, that is the frequency at which infinite attenuation will be there, that is equal to cutoff frequency divided by square root of 1 minus m square, right? So from this we can get the m. So when you decide the f infinity and when you have fc, that is of constant K filter, what you will have, you can get the m as per your requirement of f infinity and fc. Okay, so for sharp cutoff, f infinity should be near to fc. Yes or no? Because at cutoff frequency the attenuation is going to change in case of low pass filter or even for high pass filter. But in order to have sharp cutoff or sharp attenuation, this f infinity, that means what is meant by f infinity? The frequency at which infinite attenuation will be there. That means it is sharp. Okay, if you see the characteristic, you will understand. So for that purpose, this f infinity should be near to fc. So for the smaller value of m, the F infinite comes close to Fc. That's why the M value should be chosen low. And the M-derived T section low pass filter is shown in this particular diagram 15.32. Right? Now, so here in this diagram, the Z1 is replaced with L, that is inductive element, and Z2 is replaced with capacitive element. Okay. So similarly for M-derived pi section also we can get all these things. So the inductance and capacitance in the series arm constitute a resonant circuit. So right, because there you will get parallel resonance, and again the condition will be inductive reactance is equal to capacitive reactance. So there, with that particular condition, you will be getting F naught, which is nothing but F infinity, like this. So this is with respect to pi section, and in case of pi section, again low pass filter Fc is 1 by pi root Lc, and F infinity will be in relation with Fc will be coming like this. Okay. So here for both M-derived low pass networks, F infinite is greater than Fc for positive values of M. That means when M is chosen between 0 to 1, you will be getting F infinity greater than Fc. Right? So accordingly we can draw the characteristics. So here again you can see the pi section of low pass filter and the two M-derived one. So if you observe the characteristic now, this is very important, because from this only we need to design the M-derived filter for this purpose only. So if you observe, we got F infinity greater than Fc. So at F infinity what happened? The attenuation is going to become infinite. So that means this change is happening a bit rapid. So the attenuation is increasing because it has to become high, very high in stop band, because it has to attenuate, right? So in the pass band it should be 0. So till the cutoff frequency it is 0, but after the cutoff frequency it is taking very less frequency band for reaching to infinite, right? This is about the logic behind the M-derived filters. So what it is saying here, the variation of attenuation with frequency is shown in the figure, and it is seen that the attenuation rises abruptly, becomes infinite at F infinity, and then decreases for M-derived filter. Okay, so at the same time you can go back and check the constant K low pass filter and its characteristic. What is the difference? Then you can understand the importance of M-derived filters. So therefore an M-derived filter gives a sharp cutoff. The decrease in attenuation for frequencies higher than F infinity can be avoided by connecting an M-derived filter and a constant K filter in cascade. So these things are not required. So it is saying even though at infinity it is becoming infinite, again after infinite it is getting reduced, which is not desired. So to avoid this, we can even use the cascade connection of the filters. Okay, that is not there in the syllabus. Fine. Now we can also have the variation of beta with frequency, which is shown in the figure, and we will be getting this for variation of phase constant beta with respect to frequency in case of low pass filter. So similarly we can get the variation in characteristic impedance with respect to frequency. So it is given here. Fine. So you can still observe that the characteristic impedances are varying, they are not fixed. Fine. So even though we are not able to achieve the desired characteristic impedance here using the M-derived filter, we are able to achieve the condition of sharp attenuation. Okay. So this is all about M-derived low pass filter. Further we can see the M-derived high pass filter. Thank you.